Earth, wind, fire, and water. Can you imagine that people actually believed that these were the only 4 elements in the universe for almost 2,000 years? We know that this is not true, right? But how do we know this? How did mankind change a belief of almost 2,000 years? Simple, really. They studied chemical reactions. Hi there, I'm Diasha, and together we're going to be doing exactly the same thing. Investigate chemical reactions. But you've started already in the first series on chemical reactions. In this lesson, we will recap on some of the important things we've learned in Chemical Reactions 1, and the periodic table is always a good place to start. Firstly, we found that the elements on the periodic table can be divided into 2 main groups. Metals and nonmetals. We discovered that by far the largest of these 2 groups were metals, and began our investigations by asking ourselves, where do we find metals in nature? The answer, of course, is in the Earth's crust, in the form of rocks, and we retrieve these metals by mining economically viable ore. Do you remember that we said that some metals, like gold, are found in their elemental form, while others have to be extracted from complex compounds? Well, later on in this series, we will solve the puzzle of the reactivity of metals and find out why that is. But first, let's remind ourselves of the different groups of metals that we identified on the periodic table. We looked at the group 1 metals that are also known as the alkali metals. In this group, we used lithium, sodium, and potassium in our experiments. From group 2, or the alkali earth metals, we used calcium and magnesium for testing. We also looked at this large group of metals known as the transition metals. From this group, we tested iron and copper. When we did our experiments, we wanted to compare the way in which the metals from each of these groups reacted with the nonmetals, oxygen and water. Do you remember what we found? All the metals we tested burned in oxygen with a distinctive colored flame. For all the reactions, the product was a metal oxide. These metal oxides of the alkali and alkali earth metals were then dissolved in water, and we found that they formed a basic solution called a metal hydroxide. We used red litmus paper as an indicator to show that the solutions were basic. Can you remember what the results of these reactions told us about the reactivity of the metals that we tested? In both Group 1 and Group 2, we found that the reactivity increases from top to bottom of the group. In this way, potassium is the most reactive of the Group 1 metals, and calcium is the most reactive of the group 2 metals. The transition metals are far less reactive than either the group 1 or group 2 metals. Indeed, it seems that the reactivity of the metals gets less and less as we moved from left to right on the periodic table. For the second phase of the investigation, we reacted the alkali and alkali earth metals with water, and the results of the experiment done with the group 1 metals were spectacular, even explosive. Do you still remember potassium spontaneously exploding when it reacted with water? Once again, all the metals we tested produced similar products. A metal hydroxide was the one product and a gas the other. There is another very important skill that you learned during the first series on chemical reactions: writing balanced chemical equations. I cannot emphasize enough how important it is to practice this skill. So let's recap how it is done. We have asked a learner to help us with this, and we will use the reaction of copper burning in oxygen as an example. We know that metals burn in oxygen to form a metal oxide. So our first step is to write a word equation for the reaction. Copper plus oxygen react to form copper oxide. Step 2 is to change the word equation to a chemical equation. The symbol for copper is Cu. Oxygen O is always found as a diatomic molecule, and one copper atom reacts with one oxygen atom to form copper oxide. Lastly, we have to count the amount of atoms of each element on each side of the arrow. We can see that we have only one oxygen atom in the product, but two as reactants. If we add another copper oxide particle to the product, the oxygen atoms are balanced. But now we have two copper atoms in the product and only one as a reactant. If we now add one more copper atom to the left of the arrow, our equation is balanced. The chemical formulae of compounds and molecules are dependent on the rules of chemical bonding. Do you know where these principles come from? In 1916, a chemist, Gilbert Lewis, came up with a theory. He said that chemical bonds were formed because valence electrons from the atoms interact with each other. Lewis knew about electron orbitals. He realized that atoms like to have their outer energy level completely filled with the maximum number of electrons allowed. Therefore, atoms that don't have complete outer energy levels react with other atoms to transfer or share electrons. In this way, they complete their orbitals. Lewis's theory is the basis of modern ideas about chemical bonding. The one thing that we did not do in Chemical Reactions 1 is investigate the reactions of the transition metals with water. To help us with these experiments, I will cross over to our friends in John's lab.
Oh, hi everyone. I've got a wonderful surprise for you today. I'd like to introduce you to my new assistant, Sepal. Welcome, Sepal.
Nice to be here. Hello, everyone.
You want to see the reactions of transition metals in water. Sorry about the mess, we'll need to clear that away. While I do that, Sepal, can you get me 2 beakers filled with water? Now, in today's experiment, what we're going to do is we're going to take the copper and put it into water, and then take this iron nail and put it into water. And let's see what happens. We might have to wait a little while. Can you see anything happening?
No, it still looks the same.
Well, Diasha, nothing much seems to be happening here. We have to go now, so we'll put this aside, and next time you come and see us, maybe there will be some results. Bye.
Thanks, John. Well, that was rather disappointing, but not really unexpected. We already saw very little reaction with magnesium and water in our previous series, and we know that transition metals are less reactive. Anyway, like John said, maybe we will see the results when we visit them next time. I just hope he doesn't throw out our experiment. See you for our next lesson, when we will talk about steam.